Hi, this time I'm going to be working from section 4.2. I'll work on problem number 35. And this gives us the problem where we're told that y equals at squared times e to the negative bt for t values greater than or equal to 0. We're told that a and b are positive constants, and they want us to find a t value to maximize y. So we know we're going to have to find the first derivative because when the first derivative is equal to 0, those are our critical points where we have potential maximums or minimums occur. So the first thing I need to do is find y prime. And I see here that I will be using the product rule. And so the product rule tells me that I take the derivative of the first function there, and I get 2at and multiply that times e to the negative bt. And then I add to that the first term, at squared, multiplied by the derivative of the second term. Notice the derivative of the second term is going to require that we use the chain rule. So the first thing I do is take the derivative of the outside part, e to the negative bt, and then multiply that by the derivative of the inside part. That gives me negative b. So a little bit of review there on the product rule and the chain rule. Okay, so now let me go ahead and just clean this up a little bit. Y prime equals 2at e to the negative bt minus a bt squared e to the negative bt. And I'm going to be setting that equal to 0 so I can find those critical points, find those potential turning points. And so I say 0 equals 2at e to the negative bt minus abt squared e to the negative bt. And that is hard to do unless I find something that I can factor out so that I have two terms being multiplied together, because then I can use the fact that any number multiplied by 0 is 0. So I'm going to do that. I'm going to factor out the e to the negative bt. And that leaves me 2at in my first term minus abt squared. Okay, so now I know that either e to the negative bt equals 0 or 2at minus abt squared is equal to 0, or potentially both, but in this case, this e to the negative bt can never be 0. E to any value at all can never be 0, so this is not possible. So that leaves us over here that we have to figure out what would make this expression here equal to 0. So again, I'm going to do a little factoring. So I can factor out, I see both of these terms have an a and a t. So I can say at times 2 minus bt equals 0. So that means either a times t equals 0 or b minus 2t equals 0. So this would happen, this at equals 0 when t equals 0, so that's good. Then over here, b would equal 2t, so t equals b over 2, and that is the other critical point. So I have this critical point, a critical point at t equals 0, and a critical point at t equals what did I do wrong here? 2 minus bt. Okay, yeah. Sorry about that. I am going to erase this because I switched. I had a little bit of dyslexia there when I did that. It would be 2 minus bt equals 0. You see how easy it is to make these mistakes. And so then I end up with 2 over b is equal to t. And that makes it much better. Okay. And so we want to find out which of these points is a maximum point. We want to actually find the t-value that would make this point maximum. And so what we need to do is come over to, I'm going to use the first derivative test, which remember I draw the little number line and I put my critical points on, 0 and 2 over b. And then I have to test some points to the left and right of these critical points. Okay, first of all, remember though that t has to be greater than or equal to 0. So I'm really not going to check anything to the left of 0 because that's not part of my function anyway. So I need to try some values that are larger than 2 over b and smaller than 2 over b. So I'm going to start with the value 1 over b, because 1 over b is less than 2 over b. And so if I go back to my derivative here and plug in the value of 1 over b for t and see what I get, okay? So before I do that, I'm going to kind of draw this out a little bit so I can look at it more easily. So y prime is equal to e to the negative bt. I'll pull that out to the front. I also see that I can pull this a and t out to the front, and that leaves me with just 2 minus bt left. So see, I pulled out the e to negative bt, I pulled out the a, I pulled out one of the t's, so that leaves me with 2 minus the bt left here. And this is the what I'm going to use for substituting in this 1 over b. And now when I do that, let me change colors so you can see more easily. This term here, when I substitute 1 over b in there, I'm going to get a positive. Actually, no matter what I put in for b, for t, I'm going to get a positive value because e to any power always returns a positive value. Then when a is positive, so when I multiply a times 1 over b, which is also positive, this becomes positive, this becomes positive. So the only thing I really have to look at is what's going on over here. So if I have 2 minus b times 1 over b, that would give me 2 minus 1, which is a positive. So positive times positive times positive gives me a positive value here, which means my original function is increasing. Okay, now let's try that again. Let me change to a different color so that I can look at a number like maybe 3 over b. 3 over b is bigger than 2 over b. So let's try that. And again, no matter what, this first term is going to be positive, this second term is going to be positive. So I just need to look at this 2 minus b times 3 over b, which would be 2 minus 3, which is a negative value. So positive times a negative gives me a negative, which tells me my original function was decreasing, which tells me that when t is equal to 2 over b, I have a maximum. So this is indeed my local maximum. Now, what happens at t equals 0? Well, at t equals 0, that is not going to be a maximum value for me because I can see that my function is increasing. And so definitely whatever's going on at 0, it is not going to be a maximum. So there's my answer.